Hello and welcome to the Data Engineering Podcast, the show about modern data infrastructure. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at www.dataengineeringpodcast.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your data pipelines or trying out the tools you hear about on the show. Go to dataengineeringpodcast.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. And to help support the show, you can check out the Patreon page, which is linked from the site. To help other people find the show, you can leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host is Tobias Macey, and today I'm interviewing Justin Cunningham about Yelp's data pipeline. So, Justin, could you please introduce yourself?
Sure. I'm Justin Cunningham. I lead the data pipeline team at Yelp. I'm a software engineer here. I've been at Yelp for about 3.5 years and started the data pipeline project and have seen it through to where it is today.
And how did you first get interested or involved in the area of data engineering or data management?
So I first got involved in data engineering or data management, primarily driven by application needs. So I started off effectively working on experimentation infrastructure. And data engineering and experimentation are really interrelated because to run experiments effectively, you need access to rich and accurate data. In addition to that, at Yelp, I started working on data warehousing and also on our metric system, and we had a lot of duplicative infrastructure between those two projects. So I was able to kind of get started by taking a look at what infrastructure we had and trying to rationalize it into a more robust, more centralized piece of infrastructure.
And can you start off by giving a brief overview of the overall pipeline and the kinds of data and workload that you're optimizing for?
Sure. Our overall pipeline is centered around Apache Kafka and a schema store. So the schema store has got information on which topics or streams that we're publishing to and what schemas are used to encode data that goes into those streams. Outside of that core, we have a variety of other applications that are accessing the core and writing data into it and reading data out of it. You could roughly divide those into consumers, producers, and transformers. Consumers would be applications that are consuming data from Kafka, from the data pipeline, and doing something with it. A good example of that would be we have a Salesforce connector that reads data from Kafka and writes it into salesforce.com through their APIs. We also have a connector that reads data from Kafka and writes it into Amazon Redshift, another that reads data and writes it to Amazon S3. On the producer side, we have applications that are producing data into Kafka. Concretely, a couple of examples there would be a producer that reads data from MySQL changelog and produces it into Kafka so that we're able to access that data and see what changes have happened. So it's effectively a change data capture system. Outside of that, on the transform side, we have systems that read data from Kafka and write it back to Kafka, doing some sort of intermediate transformation. We use this to decorate data, to make it more legible externally if it's coming from an internal system with some kind of specialty encoding, and generally just to clean up data or make it more accessible.
From reading through the blog posts that you guys have written about the overall process of coming to this final architecture, I was seeing that you had originally had a more sort of monolithic and ad hoc method of managing the data throughout your system. So I'm wondering if you can describe some of the impetus for tackling this overall project and re-architecture of your stack and the way that the data flows through it.
Absolutely. So early on at Yelp, the team that I was on originally was called the BAM team. It stands for Business Analytics and Metrics. And that team maintained a few different systems. One of those systems was Yelp's data warehouse. And what that was doing is effectively ETLing data out of the primary Yelp database and then putting it into a Redshift database so that we could access it more efficiently for analytics queries. Another piece of infrastructure that the BAM team maintained was something called the Salesforce field fillers. And that was a infrastructure system designed to move data from the Yelp primary databases into Salesforce. And the third system that the BAM team maintained was a metric system. And the metric system was just calculating some aggregate values on top of the Yelp primary database and actually reinserting it into the primary database for display. It was kind of a business intelligence system. So it was effectively computing metrics on top of the Yelp databases to try to figure out how the business was performing. The rationalization step there was effectively looking at what system overlaps there were. And in principle, both the Salesforce connector that we had and the data warehouse ETL system were very, very similar. They're reading data out of the primary databases, doing light transformation on it, and then putting it somewhere else. Well, they're very similar in concept, but they weren't sharing any code or any infrastructure. So we were maintaining two sets of infrastructure to read and transform data, even though it was doing basically the same thing. And each one had a different set of limitations. So doing something about that started to make a lot of sense. The other thing that we were looking at was the metric system, which was, as I said, just reading from the primary databases and calculating aggregates. Well, it's not really efficient to calculate aggregates against MySQL and to do analytics queries against MySQL. We already have a data warehouse with Redshift, so it made sense to start migrating our analytics queries on top of Redshift, where we could get query performance and be able to do better exploratory queries and answer our questions a little bit more quickly and correctly than we could on top of MySQL. So in effect, we were able to go from having three disjoint systems to having one unified system where we're doing change data capture and taking that change data capture and then putting it into output systems, where output systems would be Redshift and Salesforce to replace our existing systems, and then moving the metrics problem that we had before from running directly on top of MySQL to running on top of the data warehouse, where it can run a lot more efficiently.
And while you were going through the process of picking all the different pieces of the pipeline and figuring out how they were going to hang together, I've got a couple of questions in there. One of them being, what are some of the dead ends or false starts that you experienced while going through that overall process and trying to come up with a workable design?
So the dead ends and false starts that we experienced, I think we actually did a really good job of minimizing the number of those. And I think we were able to do that pretty effectively by doing a lot of pre-planning. So one of the things that I did before we started the project is I read a lot of academic papers, mostly coming out of LinkedIn, around their data infrastructure and how they'd solved a lot of similar problems. In particular, LinkedIn had a system called Databus that was capturing the stream of changes from databases and then making them available. And after that, they'd written Kafka and done a lot of log processing with Kafka. And it seemed like what we wanted was somewhere in between Databus and Kafka. And in exploring that space, it kind of became clear that actually a lot of the new Kafka features were targeted at being able to do a lot of the kinds of things that you could do with Databus, in particular log compaction. So I think in general that our overall system architecture hasn't changed substantially since it was laid out in the initial design docs. So we actually didn't have very many false starts in this. Maybe one of the bigger ones that comes to mind is a time effectively where we were planning on using Apache Storm for most of the real-time processing. We ended up moving off of Apache Storm because we couldn't quite get enough performance out of it in Python. And we ended up doing a little bit of custom stuff. And at this point, we're looking at using Flink to work around that. So I think we got not very far down the road with Storm, but certainly a little bit further than I'd like with something that we ended up ultimately not using. But otherwise, I think we actually did a remarkably good job of laying out a fairly comprehensive plan early on and then not deviating from it very much.
And while you were going through the process of coming up with that plan, did you go through a lot of iteration cycles of getting buy-in from the team and reviewing the plan before you started doing any implementation steps to try and see if people could come up with weaknesses? And then also, I guess, how far outside of your immediate team did you go to try and do requirements gathering from the sort of final consumers of the data across the business?
Yeah, so overall, with this system, there was a very, very extensive planning process. And I think this is true at Yelp in general. On our engineering team, we do something called SEP writing. And a SEP is a code enhancement proposal. It comes from Python enhancement proposals, because we're primarily a Python shop. So the basic idea there is that if you want to build some kind of system, you do a relatively short write-up. I think the data pipeline SEP was less than 10 pages on what the system will be, what the requirements are, what problems it's trying to solve, how it will solve them. And it's not really a technical document necessarily, or at least it doesn't go into lots and lots of technical detail. It's more about the requirements and how the problem will be solved. For the data pipeline, there were quite a few teams involved in the planning process and involved in the feedback process. I would estimate probably 15 different teams were involved at some point or another in either requirements gathering or signing off. One of the other things that we did in that project, which I think was a little unusual at the time, for Yelp at least, was reaching out to other companies in the space and seeing what other people were doing. And we invited some folks into Yelp to talk a little bit about what had gone well for them and things that they'd change. And I think in doing that, we were able to expose a lot of the caveats. And I think that's actually why the project didn't have that many real speed bumps, because we were able to expose so many things that other people had tried and either succeeded at really well or didn't succeed at as well very early on in the process. So we were able to make lots and lots of design time adjustments. And because there was so much feedback across the organization, I think we were able to get a lot of different perspectives on what the different problems were and how we would solve them. And actually, this project started immediately as a cross-team effort. Our spam team was as interested as the BAM team in solving some of the challenges around moving around bulk data. And I think we, on the BAM team, concretely had really good use cases for it. So we had a wide swath of things that we'd want to be able to accomplish with the system. But there were definitely considerations from other teams involved as to what they would need in a final product for it to be useful.
And as you were going through the design process and figuring out what the different elements were in the overall pipeline and how the data was going to flow through it and trying to figure out which components were going to fill the various requirements, what were some of your criteria and decision-making process around the overall build versus buy, and which are the pieces that you did end up ultimately deciding to build in-house because of not having anything that specifically met your requirements for some of those various pieces?
Build versus buy for this project is kind of an interesting discussion, because at the time that we started the project, there wasn't much of a decision for almost all of the components. And what I mean by that is that when we first went down this path, there wasn't much of a space around it. There weren't a lot of products that you could buy. Confluent, the company that does Kafka, didn't exist yet. So there wasn't really much of an ecosystem at all that we could rely on. So we ended up building a lot of the core infrastructure. Some areas where we were able to use things that we didn't really buy per se, but were otherwise off the shelf. We relied on a lot of open source Python tools and packages. I think that went pretty well, effectively just leveraging some of the community's work on Kafka compatibility. We used the Apache Avro, all of that kind of stuff. But for the core system components, just because there was so little in the ecosystem at that point, there wasn't a whole lot that we could use that was really off the shelf and ready to go. That said, if we were to repeat this project again today, I think there's a lot more development in the ecosystem, and we would almost certainly end up using a lot more of the ecosystem components, building on top of the ecosystem components, extending them, or otherwise adding support. I think one of the themes that's going on today on this project is effectively looking at the ecosystem and trying to figure out what pieces of the ecosystem we can incorporate now, or for some of our components, even if we can replace them with things that have developed in open source or commercially in the interim that would make the system more robust or faster or more reliable. And I think that's the space itself is getting a lot more interesting from the perspective of having both really, really good open source projects like Apache Flink, for example, and also having more commercial support, like with Confluent and a lot of the tools that they've built, like their schema registry, Kafka Connect, etc.
And how long did the overall process take from the point where you decided that you needed to do an overhaul of your data management infrastructure to the point where you said, okay, this project is essentially complete, for whatever definition of complete you decide to subscribe to?
That's a great question. So our project, I think, is probably still not what I would consider complete, at least from a like entire system standpoint. That said, I think that the rough timeline looks like overall we were able to get something running in production within about 3 months of starting, and we took a little bit of a different development path with this product than we have with other things. And we started by building a kind of like a hackathon version of the project as a whole that we called the tracer bullet that was effectively supposed to just identify what the unknowns were in the system and give us a baseline with which to work with to figure out how to work around. So what we did is we effectively set aside a quarter and the whole team worked on building out end-to-end support for one application. It was streaming the Yelp business table and updates to the Yelp business table into Amazon Redshift. And we built every component that you would need to do that in at least a quasi-realistic way, in the sense that it was generalized, but we only built enough generalized features to work with that specific table and going into Redshift with only the schema support that we would need for that data. And we actually learned a lot from that process about what we'd need to do to support schema transformations, exactly how hard it would be to support different kinds of schema registration, what the schema store would look like. One of the things that we ended up doing at the end of that project is really discarding all of the software that we built and then rebuilding it in a much more reliable way. But the things that we learned from having hacked it together were really, really invaluable in figuring out how the whole project and whole ecosystem should really work together. So to get through the tracer bullet stage and get that hackathon version of the project built took about 3 months. And we were able to stream from that point one table from the database into Redshift. And to get from the tracer bullet to an actual production application running on arbitrary data took about another 9 months. And the first application that we ended up really building was an application that was streaming arbitrary database changes into Salesforce, so that our sales teams would have accurate business information to call out to businesses, which is pretty important at Yelp since we have a relatively large sales team, and we want to make sure that the information that they have is as accurate and as real-time as possible, so that when they're calling businesses, they're able to really have the information that they need to be able to sell them and present Yelp well. So I still wouldn't really consider that a complete system, and that's after a year of development, because we were only really able to support one use case end to end. It took about another 6 months from that point to have a second real use case online, which was our Redshift connector. And by combining the Salesforce connector with the Redshift connector, all of a sudden, all of the data that we were capturing from the databases, we're able to stream into Salesforce. We're also able to stream it into Redshift and start replacing a lot of our data warehousing needs. And then I think simultaneously, we're able to start looking at that then and saying, wow, this system is now replacing these legacy systems that we built up. And we're also starting to see some network effects from having these two disparate connectors that if you write data in this format, you can have access to both of them. And from there, we've just been building out the ecosystem more and more, building lots and lots of auditing tools, correctness tools around it, and lots of bug fixing, lots of scalability, performance improvements, that kind of thing. So I guess you could say from some extent, I would really consider it to be a viable platform and ecosystem at about the 18-month mark, but still not really done.
Yeah, software is never done until you shut it off and walk away and move on to something else.
Yeah, exactly.
And so you're saying that a decent part of the recent work has been sort of identifying and fixing bugs. So what are some of the different failure modes that you have experienced in the various pieces of the pipeline that you've built up? And what are some of the ways that you, one, identified those failures, and then two, engineered around them?
Failure modes with this system are really interesting, and I think it's worthwhile to think about the numbers a little here. We do billions of messages a day throughout the whole ecosystem. So if you're talking about seeing a 1 in a million event, we see 1 in a million events several thousand times a day. So we have lots and lots of opportunities for really, really rare edge cases to get hit. So one of the things that we did early on to help identify performance issues and other kinds of bugs and regressions, we built a pretty robust canary system where we actually maintain 2 copies of most of our production infrastructure, that we actually roll out more things with the canaries than we do with the actual production instances, because it gives us more feedback on what's working and what's not. And what I mean by that concretely is that we actually run more data through our canary than we run through prod. On prod, we only are looking at the things that we're actively using. In the canary, we actually try to push everything through it. And that gives us early feedback on what kind of data we can support, what kind we can't support, what the scalability will look like when we add more stuff to prod. We also introduce some probabilistic failure into our canaries so that as they're running, they actually are forced to fail a little bit more frequently. And that gives us some pretty nice feedback on what the failure mechanism and recovery mechanisms look like in practice. And for example, if we're introducing bugs in recovery, by introducing a little bit of probabilistic failure into our canaries, we're able to say that after a few days, we're likely to see a recovery problem. Like, our actual production systems don't fail that often, probably only every couple of weeks, perhaps. Our canary is designed to fail every 20 to 30 minutes or so, just probabilistically, and that gives us some decent feedback as to how recovery happens, if there's any issues that surface in there, and what that looks like. And I would say almost all of the actual production issues we see are really around either losing data or duplicating it excessively. And really that boils down to state saving and failure recovery and error handling. And I think those are really, really challenging problems to solve in distributed systems in general. So a lot of our focus as a team has been on building up knowledge around how to resolve those issues, building up tooling to make going from some kind of known problem, or at least some kind of known symptom, back to what the actual problem is something that we can do pretty easily, and otherwise getting enough introspection into the system that we can understand if it's mostly working or not. So I think that there's still a lot that we could do there, but I think we've gone pretty far down the path of doing things kind of like what Netflix was doing with Chaos Monkey, and that's been fairly helpful in identifying problems, and otherwise just keeping systems online, running lots and lots of systems, running lots of events through them. I think all of that helps expose issues early and often.
And what are some of the tools and processes that you're using to be able to the deployment and maintenance of the various pieces of the overall pipeline? And what are some of the techniques and tooling that you're using for monitoring the overall availability and accuracy of these systems and the data that flows through them?
So for doing deployment and monitoring uptime, really, I think the solution that we've come to for availability and uptime as a company has been building out a platform as a service. We actually open sourced that a while ago. It's called Pasta. And effectively what that does is it takes Docker containers and deploys them with Marathon and Mesos. And almost every service at Yelp today, and I think it may be every service at this point, is deployed on top of that platform. And what that allows us to do is to kind of treat any piece of code we have as a container with all of the benefits that entails. So during our build process, what we do is we actually spin up a bunch of containers that simulate, or in many cases are, the real thing. So we spin up real Kafka, real Zookeeper, and we run integration tests with the actual containers that we're going to deploy to production. And only if those containers pass the integration test do we end up deploying them. We do that for almost every service at Yelp. So it's not something that's very specific, but I think it works reasonably well at catching these kinds of problems. Running the actual code that you're going to deploy where there's no ecosystem or environment differences. You're just taking the same container and sending the same bytes out to the machines that are going to run them. That's worked pretty well. From an application side for monitoring, we use something called SignalFX to get graphs, and we generate lots and lots of time series charts that are all kinds of different stats about the system. And that could be things like how far behind we are, what the difference between the current time is and the event time that the system is processing, and additionally things like throughput inside of our consumers and producers, like how many messages are we doing per second, what schemas are associated with those messages. So we can say, for example, that we're reading in 5,000 messages a second with this schema ID, and we're outputting 50 messages a second for this schema ID from this worker. And then we can kind of get some nice time series graphs to show in processing time how these systems are actually operating. We do some things with technology called Sensu. That's what we use for our alerting, that effectively does active alerting based on different things that we're triggering from application code. So, for example, one thing that we trigger on is how far behind event time we are. So inside of our producer, it actually looks at the event time that's set on inside of our messages and the current time. And if those drift too much, we can configurably send an alert and page the team that owns the infrastructure. I think at this point, one of the things that we're starting to get into more and more is looking at additional auditing that we could be doing. And what we're probably going to start doing is writing auditing messages from our consumer and producer implementations that would log for every event time window, how many messages are we consuming, how many are we producing, and how does that map to upstream and downstream systems. And I think with that information, we'll be able to kind of get a more holistic view of how messages are flowing through the system, where we're missing data or where we're duplicating it, and how effectively an upstream and a downstream map together and what that looks like.
And while you were going through the overall process of switching out some of the production components as you were building out these new pieces, what were some of the ways that you made sure that you weren't starting to introduce new failures or new error cases into the system and verify that the data that you were getting out was the same that you wanted or better?
Fortunately, at Yelp, we had already had a number of systems in place to audit, I would call it maybe data reliability across system. And because we were already doing some light ETL, we already had a number of systems that could look at, say, an input and an output, and at least say at a high level if they were pretty close to each other. So initially, we were able to leverage a lot of that. What we've gotten more and more into as time has gone by, and this is extremely helpful for debugging, is auditing batches and auditing processes that can look at a specific system's input and outputs and do some static verification on those. So to give an example of that would be something like a transformer that we're doing from a Kafka topic to a Kafka topic. So what we might do is write a batch that will look at the input Kafka topic and the output Kafka topic and try to match up the messages between them and see that there aren't things that are drifting. And then overall, what we'd like to do with that kind of thing is both use it for debugging. So in the event that we find some missing data, we can trace back and see exactly where in the process that data went missing. And also, we'd like to start scheduling some of those things and running them probably probabilistically on top of the overall data. So we could kind of say, let's take the 30 or 40 most important downstreams and trace back through their dependencies, and with some fairly low probability, check their dependencies every day and see that whatever we got in, we actually got out, and just kind of doing some sampling to see if we're actually maintaining the invariance that we've set for ourselves. So it's kind of like a double duty approach for a lot of the tooling that we've been writing for auditing to make sure, one, that we're not losing data as the systems are running, but two, if we do have some kind of data quality problem, to be able to quickly debug it. And once we identify where the problem is, to be able to ideally work backward from we're missing this data which came in this batch to here's where in the operational logs this data went missing, and here's the concrete reason why that happened, so that we can further solidify the system.
And one piece that I've been wanting to dig into a bit more is in the overall schema management and data serialization. I noticed that you ended up settling on Avro as the transmission format. So I'm wondering if you can dig a bit into what are some of the other serialization formats that you considered for the project, and what made Avro the right choice for you?
For serialization formats, we looked at a number of things. I think Avro was an early leader primarily because of the amount of ecosystem support, especially around Kafka itself, and in particular with LinkedIn's experience with Avro. So I personally was pretty set on using Avro fairly early on because of the experience that LinkedIn had had with it. That said, we had a pretty extensive project looking at different schema formats, and we considered protobufs and thrift, and also JSON, and a variety of things that use or provide schemas for JSON files. And I think ultimately that there were a couple of things that we really liked about Avro, which is why we ended up going with it. I think the first, and maybe one of the most significant, is that with Avro, the schema is an artifact. And it's really kind of like a piece of data in itself. An Avro schema is just literally JSON that describes what the data looks like. So with it being just JSON, we're able to store it and transmit it as JSON from an HTTP service, which fits really nicely with Yelp's general SOA and RESTful kind of services. And really, that's all our schema store is. It's a RESTful service that returns JSON, where the JSON is a Avro schema. And that fits really well with the pattern that we have here. I think as we looked into some of the other serialization formats, occasionally what we'd want to do, or maybe even in some cases be required to do, is provide something more like a Git repo that had a bunch of compiled schemas in code, where you would have like serialization and deserialization code. And if you wanted to use a schema, you'd have to include that package and then pull in the schema code and use that for encoding and decoding. One of the things that we really wanted to accomplish with the system overall is allowing a consumer to decode a message with a schema that didn't exist when the consumer started. So in order to support that, the consumer really needs to be able to fetch the schema or fetch code that could decode the message after it starts running. And I think it's kind of undesirable to, fetch actual code and exec it or something like that, compared to fetching an artifact like a JSON doc that's representing a schema. So that's kind of how we landed on that. The other thing that I would point out about Avro that I think we were really kind of keen on is the different kinds of casting support. So one of the things that you can do with Avro, you can give it a different reader schema and writer schema. And if you give it schema that are compatible, the writer schema is the schema that was used to originally encode the data. The reader schema can be any compatible schema. And what will happen is that Avro internally will figure out how to map however the data was written into however you're trying to read it. And we use that to provide some invariance on our Kafka topics. What we're able to really do is say that if you start reading from a Kafka topic with a reader schema, any schema that ever writes into that topic will be compatible with all of the reader schemas that have ever been used with that topic. So you'll never get a situation where you have data in that topic that you can't continue reading. And that lets us do a lot of really, really powerful things around compatibility, where like one of the biggest issues that I think we faced previously at Yelp in general with data processing, and in particular with log processing with JSON, was schemas changing without the downstream consumers knowing. And this more or less completely resolves that problem, because you're always guaranteed to be able to continue reading that data. We do some workarounds for dealing with incompatible schema changes, but that's very explicit compared to making a implicit change to a JSON file and then eventually a consumer breaking in production. This is the kind of thing that we can actively alert on instead of, for example, waiting until it's a real production issue.
And throughout the course of performing all of this design work and implementation, was the original plan to open source the end result, or was that a decision that was made as you came closer to a more cohesive system and realizing that there were pieces that could be more generally useful outside of Yelp's particular use cases? And then once you did come to the conclusion of open sourcing what you had, what were some of the challenges associated with making sure that the pieces that you were releasing were properly structured so that they could be used by people outside of Yelp without necessarily having to replicate the entire ecosystem and infrastructure that Yelp is using?
For this project in particular, I think that we did not actually intend to open source it. And in retrospect, I think there's a lot of things that we would have done differently had we intended to open source it from the beginning. Concretely, we ended up building on a lot of internal tools and packages and really fitting it in well with the Yelp ecosystem. The flip side of that, though, is that it works less well externally because of that relatively tight coupling with the way that Yelp does software. And actually, the reason that we ended up open sourcing the system was really to give some other examples of how we solved some of the problems, more for the benefit of people that are developing other things open source. For example, like the Debezium project, I think there's probably some crossover between what they're doing and what we've done in many cases. And I think we've solved a lot of the same issues. So I think the hope in open sourcing it was more that some of the work that we'd done there would be useful in other people implementing things in the open source ecosystem than something that you'd necessarily want to run directly because of that tight coupling with the Yelp ecosystem and infrastructure. If we were to do this again, I think, especially given how limited the development was in open source, and this kind of goes back to the build versus buy question at the start of the project, I think what we'd likely do if we did it again today is build it as an open source first project. I think, hindsight being 2020, it's easy to say like, oh yeah, we definitely should have done that to begin with. But at the time, it seemed like kind of unclear that other companies had the same sorts of problems around streaming, and also how developed a streaming ecosystem would become in a relatively short period of time. So I actually think that what we've done is less than ideal as far as the open sourcing stuff. And had we done it today, we'd probably have taken a pretty different approach. But in any case, I still hope that it will be useful, at least some of the concepts for people implementing other things. And again, I really think Debezium could be a great example of that, especially with some of the stuff that we've done around being able to do consistent snapshots of databases while they're running without blocking or anything like that. I think that work in particular is something that could be extended to other places.
So for anybody who's facing a project that's similar in scope or intent, whether it's for a greenfield project and they're just trying to figure out what are the different pieces of infrastructure that they're going to need or the ways that they're going to be manipulating or interacting with their data, or for somebody who has an existing system and they're trying to retrofit a data pipeline and data management architecture into it, what are some of the pieces of advice that you would have for anybody undergoing that general process?
So the general advice that I would have on retrofitting a data pipeline or starting a data pipeline kind of project would probably be to really take a hard look at the infrastructure that's been developed in open source in the last couple of years. I think in particular, a lot of the stuff that Confluence developed is of really, really high quality. Kafka Connect and their schema store and a bunch of the other open source infrastructure like Flink, Apache Beam, etc. I think all of that is something that can be built on really, really, really easily today compared to the situation that we were in about 2.5 years ago when this project started. So I think if I were looking at this today, I would definitely start with a pretty thorough overview of what exists in stream processing. The other thing that I would point out is that just in general, distributed systems are pretty hard to get right. So it's really easy to look at systems and say, oh, this looks like it's going to be relatively simple. But I think for a lot of the stream processing stuff in particular, it ends up being a lot harder and taking a lot longer than anybody kind of initially thinks. So I would definitely caution that on the build versus buy side, almost certainly look really, really hard at the buy side today. It's much more developed than it has been in the past, and I think it's getting better all the time. And contributing to that, I think is a great way of reducing costs and getting faster time to market, and also reducing some of the ongoing maintenance costs. I'd point out that software maintenance in general is probably 67% of the total cost. It's something that we talk about at Yelp pretty regularly about, especially when making the build versus buy decision, that if you build it, you then have to maintain it. And that's actually much more expensive than just the part of the project where you're building it. So if you're not accounting for that, it can kind of skew things pretty significantly. I would definitely caution before building lots of infrastructure here and really try to use what the community's already built and extend it if possible.
So are there any pieces of the overall project or infrastructure that we didn't touch on that you think we should cover, or any additional subjects that you think we should talk about before we start to close out the show?
So in general, where we're going with our infrastructure at this point is really into advanced stream processing. And what I mean by that is using tools like Apache Flink and Spark Streaming and Apache Beam to provide a more rich set of primitives on top of stream processing so that we can do really advanced real-time computations and start doing real-time analytics, and ideally to start doing some real-time SQL. And I think there's a lot of opportunity with real-time SQL to really change the way that a lot of modern data infrastructure is built. And one of the things that came up at the Kafka Summit that was pretty recently going on in New York was the Confluent folks effectively saying that streaming could be as big as databases and maybe bigger than databases. And I think that's actually true, especially when the primitives get a little bit better. And the way that I kind of see that going is as we start developing some of the stream SQL stuff, being able to convert a lot of the things that were batch-oriented previously and relatively difficult to write, kind of expensive to run, into just very simple stream SQL implementations that are running in real time and spitting out results as they come in. And I think that's going to enable a ton of new applications and also potentially reduce some cost and complexity. I think it's much easier to think about something like a streaming SQL statement than something like a MapReduce job. So we're looking actively at that, and I think overall there's been a ton of progress, even in the last 6 months in Apache Flink on stream SQL, and I think that's one of the most exciting areas, and that's where we're going to be spending a lot of time in the next year.
Okay. So for anybody who wants to follow the work that you're up to and get in touch, what are some of the best ways for them to do that?
The Yelp engineering blog is pretty much updated once a week or so, and that's got a lot of useful information about what's going on at Yelp. And we try to write up all of the major infrastructure projects that we're doing on there. So that's a good way to stay up to date on what we're doing. I'm personally always happy to answer questions or talk to other people that are working on this stuff. My email is justinc@yelp.com. So if anybody has questions, I'd be happy to talk.
Great. Well, I really appreciate you taking the time out of your day to share some of the lessons that you've learned and work that you've done in this overall process. It's definitely a very interesting subject area, and one that it's often easy to find bits and pieces of the overall experience in various blog posts from different companies, but trying to get an overall sort of holistic view of this kind of project from start to finish is usually fairly difficult to come by. So it's definitely great that you took the time to share it with us, and I'm sure a lot of people will be interested to hear about some of the sort of deeper details that don't necessarily get covered in a blog post.
Yeah, absolutely. Thanks for having me. I'm definitely looking forward to hearing about all kinds of data infrastructure things now and in the future.
Great. Well, thank you again for taking the time, and I hope you enjoy the rest of your evening.
Thanks. You too. Goodbye.